So what are the properties of simple harmonic motion? As was mentioned earlier, for vibrations to be simple harmonic motion, they need to follow a simple sine function. When we say sine function, a sine or a cosine, that's the same thing. Now, what do we mean follow a sine function? That means the position, if we draw it as a function of time, like we have here, it's going to look like a sine function, like you see here. Now, the expression then for the position as a function of time is going to look somewhat like this. I will show later how you can write this as a function of sine instead of cosine as well. What we have as A, that's the maximum displacement from the equilibrium position. We call it the amplitude. That's why we have A. That's if we start a spring into vibration by pulling it by an amount A and letting it go, that would be the A. That's if we just pull it and let go. Or if we just compress it by an amount A and let go. That's what we get. That's our expression. We'll talk about the details of what we use for T and phi later on. Now, omega is what we call the angular frequency. F is what we call the frequency. That's the relationship between them. Omega is 2 pi f. F is how frequent are the oscillations, like how many per second. T is the period. The period is the time for one full oscillation. So if we look in a graph of x versus time, that's the time for a full oscillation. That's from here to here, or from here to here, or from a crest to a crest, or from a trough to a trough, or any position on the wave to the equivalent position on the wave. The time for a full oscillation is what we call the period. The frequency is the inverse of the period. Now, if our position is given by that, the velocity is going to be minus A, the amplitude that we have for the position, times omega. Omega is, you see it as an argument here. We have omega t plus phi. You see it as an argument of the cosine function. So it's going to be here as an argument here as well, but then also in the amplitude of the velocity. A omega is actually V max, or the amplitude of the velocity. If we draw the velocity as a function of time, it's going to look somewhat similar to this. If I'm going to draw velocity versus time, so it's going to look somewhat like this, with this being V max being equal to A times omega. Of course, it's going to have the same period as the position graph. So the velocity has the same period and the same frequency and the same angular frequency as the position. The acceleration is going to be given by minus A omega squared cosine of omega t plus phi. Notice here that my maximum acceleration, or the amplitude of the acceleration, A max, is minus A omega squared. So it's the amplitude for the position. Remember, A is x max. So it's going to be the amplitude for the position times the angular frequency squared times cosine omega t plus phi. Now, if we factor out the omega squared, that shows us that it is actually minus omega squared x of t. X of t is this expression. Remember the condition that we discussed for simple harmonic motion. The condition was A is proportional to minus x. That's what we have here. A is equal to minus omega squared x. Recall, for a spring mass system, when we did the calculation using Newton's second law, we found that A is actually minus k over m times x. So this is telling us what omega squared is, or what omega is. omega is square root of k over m. If we know omega, since it's related to the period, we can find the period. We can find the frequency using the relationship omega is equal to pi f, or 1 over t for the frequency. So in summary, for a spring mass system, x can be expressed as a cosine of omega t plus phi. I'll discuss phi later on. V is going to be minus V max sine of omega t plus phi, with V max equal to A omega. A of t is minus A max cosine of omega t plus phi, or minus omega squared x of t. A max is A omega squared. A max also for a spring mass system is k over m times the amplitude. Omega for a spring mass system is square root of k over m, and that allows us to get the period and the frequency.